Hi, and welcome everyone to this Danfoss Drives webinar on hybridization. My name is Rich, and I'm a Senior Manager with IEEE Global Spec, and I'd like to review just a few housekeeping items with you before we get started. Let's take a moment to familiarize ourselves with the operation of the user interface for today's webinar. Now, the large window that you're currently viewing with the heading Danfoss Drives presentation in the upper left, that's the primary window for this webinar. Just to the right of that main window, you should see the speaker's bio window, and that contains background information on today's presenter. Now, just below that, you should see a Q&A window. And at any time during this presentation, you can enter a question into the box in the lower section of the window and click Submit. Your question will then be placed in the queue for our speaker to address when we get to that Q&A session. Now, if you look to the bottom of your screen, you should see additional buttons that will enhance your webinar experience. If you'd like to see what a particular button does, just hover your mouse pointer over it and a tooltip will appear with a description of that button's function. Now, for those of you who may be using Chrome or Edge browsers, if you have the Flash plugin blocked, please click on the Media Player, which is the second to last widget on the right, and then click on the Play button. Okay, at this time I'd like to introduce today's presenter, Miles Mahaffy. Miles is the Global Product Marketing Manager for Danfoss Drives. Miles studied electrical engineering at Queen's University at Kingston, Ontario, and concentrated on power electronics and controls. He began his career in 1990 in the growing drives industry in design and development. He progressed his knowledge and experience by holding positions in firmware development, applications engineering, regional sales, both in Canada and the U.S., and high-power drives product management. Miles, welcome to today's event, and with that, I think I'll hand things off to you to get us started. So Miles, go right ahead.
Hello, and welcome to the webinar on hybridization. My name is Miles Mahaffy. I'm the Global Product Marketing Manager for Danfoss Drives. During this webinar on hybridization, we will cover four main topics. First, we'll cover what is hybridization, the basic ideas and concepts, what industries and applications benefit from hybridization. Next, we'll explore some energy storage possibilities, a critical element for hybridization. And finally, we'll look at centralized versus integrated hybridization and the corresponding hardware topologies. So let's begin by looking at what is hybridization. So hybridization, a basic definition, is combining and using multiple energy sources to deliver power while maximizing efficiencies. So providing power where and when it's needed. So a good example from this would be a hybrid electric vehicle. Most people are fairly familiar with that. So in a hybrid electric vehicle, there are two energy sources, gasoline and electricity. The gasoline is converted into mechanical energy through the combustion engine. The electricity is stored in a battery and converted to mechanical energy through power electronics and electric motor. The two are then combined together through the mechanics in the vehicle to propel the vehicle. Now there are four stages that we could take a look at in the electric vehicle. If we looked at this first stage where we are running on electric only, so this is where the battery would provide all the mechanical energy to propel the vehicle. This case occurs when the combustion engine can't operate at its maximum efficiencies. So for example, if you're running at very low speeds, backing down the driveway, for example. The next situation is where you would have the hybrid or electrical assist. So this would be where you would be operating, where you would be accelerating, and the battery and the electric motor can provide additional torque and power to accelerate the vehicle. This allows then the combustion engine to be optimized for operating at a constant speed, for example. If we look at where the battery is charging here, this could be where the vehicle is operating at a constant velocity, and therefore the the combustion engine has the ability then to produce additional torque to then charge the battery during this stage, and the combustion engine then operates at a more efficient operating point. And then finally, there's where we have regenerative braking. In this situation here, we will convert the kinetic energy of the vehicle into electrical energy, and we will charge up the battery while braking the vehicle to a stop. In particular, in this last situation, with a normal combustion engine vehicle, we would have had to have dissipated that energy through mechanical brakes, which would have dissipated that energy into heat energy, which is considered to be a waste. But overall, the purpose for doing a hybrid electric vehicle is to improve the efficiencies. And that can be observed in the mileage that you can get in a hybrid electric vehicle versus a standard combustion engine. With the concept of the hybridization from the electric vehicle in our minds, let's have a look at potentially where else could we use those concepts to benefit from hybridization and energy storage. Two applications that come to mind come from solar and wind. If we look at our overall energy production and we start to consider how we meet supply and demand and what locations can we provide hybridization along with energy storage to meet those demands. We know that we will have potentially solar, wind, and maybe some other renewables that may be localized or close by our customers. However, both of these applications, solar and wind, cannot consistently and continuously provide energy for a consumer. Solar depends on when the sun shines, wind depends on when the wind blows. And in order to meet the demands of our customers, our energy production may have to change. It may have to change rather rapidly based on the changing supply of solar and wind, as well as our consumers. And in order to do that, we can do a centralized type of hybridization where we have energy storage that may be at our energy production facilities, nearer to our substations, or closer to our consumers, depending upon the amount of energy storage that we need. But it works in a similar way that the hybridization in the electric vehicle. It's about being able to meet supply and demand. I've got multiple energy sources. They may not always be able to supply that demand, which may be only instantaneous or it may be for a longer period, which we'll discuss in a little while. But in order to be able to meet that supply and demand, hybridization with energy storage becomes critical. Other applications that can also benefit from hybridization, think of marine and offshore. Marine and offshore are, in a sense, a mobile type of application, similar to the hybrid electric vehicle, in that they're not going to be tied to an electric grid. Typically, they're going to operate with a diesel engine of some kind. The diesel engine may be providing direct mechanical propulsion, or it may be in the form of a diesel genset providing electricity to the vessel. In either case, it's possible that there is excess power being generated, for example, with a main diesel engine that may not run at optimal speeds, but at low speeds to be able to provide electricity to the vessel, but if operating at full speed and full capacity, could produce additional electrical energy that could provide the entire vessel. Or it could be charging a battery on board that vessel that could be used for electric propulsion, that could be used, for example, when coming to port to reduce emissions and for silent operation, for example. Other applications we can look at, for example, could be harbor cranes. Some harbor cranes, rubber tire gantry cranes, for example, are a form of mobile application, running again from a diesel genset. That diesel genset has to be sized for peak load handling capabilities. When lifting a load and accelerating it requires a very high peak current when the load starts to get up to maximum speed. In this case, there's a requirement for increased energy. That can be from a battery supplementing the main diesel genset, for example, rather than oversizing the diesel genset to operate at a point where it's no longer as efficient. And then when lowering the load, now you can recover that energy, that potential energy that you would have normally bled off through resistors and heat becoming inefficiency. So now you can then optimize your overall efficiency in this particular application. Other opportunities, for example, could be in process industries. Think of a paper machine or a metals line. Shutting down during operation can cause serious financial losses in the overall process. So in order to be able to continue to run, it may be necessary during a blackout period or a brownout period to provide enough energy for the process to continue to either operate or to successfully shut down to minimize production losses. Same in commercial buildings. The ability to ride through momentary brownouts or blackouts in a UPS type of situation. And of course, there's other transportation opportunities, much like the hybrid electric vehicles, such as buses, trolleys, as well as more heavy-duty types of industrial applications, such as land construction and mining vehicles. All of these are examples of hybridization where you could benefit from energy storage and power conversion to optimize your efficiencies. So with that view of where we could use hybridization, we continue with the question of why. And the answer is, with energy, we need to match supply with demand. So our typical applications, if we were to look at it, first we would have a time shift for production. An easy one would be solar. We produce solar energy during the day when the sun shines, but we may have demand for energy in the nighttime. Next, we could look at is peak load shaving for incoming power. An example was accelerating the electric vehicle, providing additional peak power where the original power source may not be capable of providing that short-term power. And finally, if we were to look at it, a third one would be a backup power or a blackout start, for example, such as in those process industries where we want to be able to ride through a blackout or a brownout without having any interruption in our processes. So finally, when we look at these three applications, we also have to consider a category in terms of time. Because although we can have each of these three categories as applications, sometimes the amount of energy storage can be much longer for some applications than others. So if we look at sort of these three categories, below a minute, for example, so that's where you could be looking at on the energy side, the power regulation, so the frequency regulation, so a peak shaving, the ability to compensate for very momentary changes in peak power requirements. The next would be a power quality, so a backup or a blackout start, for example, something below a minute. So that would be considered a very momentary interruption, less than a minute. Next, we would look at something below 15 minutes, for example. If we wanted to do load leveling or capacity firming, for example. So some kind of a time shifting, maybe more along the lines of wind turbines, where the wind may be fluctuating quite a bit during a 1 hour period, where we want to level the overall load to match the demand coming from our consumers, for example. It can be considered more of a spinning reserve. So again, a backup power or a blackout start, but in a much longer period of time. So this may be a process that requires a much longer period of time to be able to shut down successfully, in which case you need to be able to provide enough energy to last for a much longer period of time. And finally, when we start to look at the above 15 minutes. Now we're looking at more on the power and energy management side. Here we're looking at peak shaving and time shifting on a much longer scale. So in these cases here we're looking at, for example, time shifting with solar. We produce all day, we may need to use it all night. It requires a lot longer period of time and potentially much higher storage. It's also possible to do, for example, a peak shaving that may be considerably longer period of time. In this case, we may have a period where the wind is completely died down for a much longer period of time, and we need to be able to compensate that for a much longer period of time. So again, we're looking at much longer time cycles. These time cycles are critical because it is a requirement that we look at this time cycle to determine what type of energy storage best suits our applications. So now that we've talked about the time characteristics of hybridization, it's important to look at the energy storage medium characteristics to make sure that they align. If we look here at this chart, on the y-axis we have the discharge time, on the x-axis the rated power, or the amount of energy storage that they're capable of and power output. If you see here we've got A, B, and C. We're trying to match them up with energy management, bridging power, and power quality. If we look here down at C, which is power quality, this has a very fast discharge time and a limited amount of power capabilities. This would be a supercap. Supercaps are extremely useful for highly cyclical, lower energy output. For an example, a good application would be a heave compensated winch on a vessel, where you would constantly be charging and discharging, charging and discharging. Very long life cycles, for example. The next we would be looking at would be a bridging power gap. Here we've got a number of potential opportunities, mostly with different types of batteries, but also with flywheels. So mechanical energy storage is also a highly viable application possibility for energy storage. And then finally, when we start to look at sort of this energy management, this much longer term storage, again, we're looking at a lot of potentials for different battery applications, but also if you look, there's also compressed air, has a lot of rated power, but again, a much slower discharge time. There are other opportunities such as hydro, where you pump a reservoir full during the day and then utilize that potential energy from that hydro to produce energy in the evening, for example, if you had a solar application. So we look again to try to match our storage medium with our categories of time. So energy management, bridging power, quality, and we look at a power to energy ratio, we can say. So if we have a very short term application, quick discharge, for example, below 1 minute for peak shaving or frequency regulation, we want a very high power to energy ratio. We need to be able to discharge very quickly compared to the energy storage. On the other hand, as we get longer in time frame, we can reduce our power to energy ratio. So we get down to much less than 2. In this case here, we have a very high energy storage compared to what we can produce for our power output capabilities. So next, let's talk about a couple of hybridization concepts. First, let's talk a little bit about the systems. So the idea behind hybridization is to solve issues in power demand, in the most effective and suitable manner. Now, that's going to depend a lot on the customer, the system, the solution for the same problem can actually be different. There can be multiple approaches to the same application. The decision to select a method is going to differ depending on a number of different things. It could be the customer's feel or trust in a particular technology, a typical type of energy storage, for example. Do they trust batteries? Do they trust flywheel storage, etc.? Availability of systems and components. There could be that this system may be installed in a location where battery supply may not be available, for example. There may be an existing system that you might want to copy. There are commercial decisions in terms of cost effectiveness, life cycle of the overall equipment. Each battery, for example, has different life cycle capabilities, charges and discharges. There are also environmental concerns potentially on the different types of batteries for recycling purposes. But overall, our suggestions are that there are two main topologies to look at when thinking about the hybridization. First is a centralized area level solution, and we'll discuss these a little bit of detail here. And the second would be a machine or system level type of solution. So let's take a look at the centralized energy storage. So the purpose of a centralized energy storage is to solve not just one potential problem, but in multiple problems. So this is where we would be connecting our energy storage directly to the grid and acting as a additional supply source. So we want to target many applications and potentially many consumers. So if we were to look at a quick sort of one line, if you will, where we may have a supply, this would be our main power generating station and our grid. We may have connected to that grid some renewables and some kind of a load, factory load, for example. And at any one point during the day, of course, there's going to be some peak power demands that are coming from our load. And it could be there's sort of negative peak power. This may be where there's no power coming from or demand from the plant, or very low demand, and yet our peak generation may be very high coming from our renewables. So we need to be able to meet this sort of average power that our main generating station is trying to supply for. So we would have here an additional energy storage where we could have potentially batteries, potentially some other form of energy storage, a DC to AC grid converter, some filtering transformer that is going to feed into our grid supply. And this is going to allow us to compensate for those peak powers or even the negative power. There's going to be a point where we'll be able to absorb the excess energy and then store that power in our storage medium. But overall, when we look at it, we are trying to balance supply and demand in a more complex application. And again, we would be on the grid itself, so we would have the ability to simultaneously meet multiple applications and multiple targets at once. So there are points where we will provide excessive additional power to meet the peaks, and there's points where we'll be able to absorb additional energy to restore it back into the battery. If we wanted to take just a quick look at which components we would utilize in this situation, it's pretty straightforward. In this case, we would have some kind of a storage medium, and then we would need an AC grid power converter. So if we were to look at a typical power converter, this would be something that we would typically deliver to our customers. This would be the grid converter section with some basic switchgear in front, LCL filters here providing filtering for power quality back to the network. And then we would have an inverter here. This is a standard inverter, so it would be the same inverter that we could use to run a motor, so a DC to AC inverter, and then we would have some connection to an external battery. Typically, batteries are going to be external. There's a reason for that. There could be additional battery management systems that are required that come from the manufacturer, for example. And this sort of simplifies the solution. This could be in an indoor type of enclosure like you see here, or it could be put into an outdoor containerized type of application, for example. Next, let's look at the other topology, the integrated topology for hybridization with energy storage. In this topology, we're going to target one specific application. So the equipment can be typically much smaller, and it's going to be sized just for that one application or one consumer. Let's look at an example. There's going to be some kind of energy supply. This could be the grid, or in the case of a mobile application, for example, marine or a crane, for example, an RTG. This could be a diesel genset providing an overall supply and AC bus. This would be my load, and with the similar issues that we had with the centralized, there are going to be opportunities again for meeting the same issues. We're going to have some peak power. For example, if I want to raise the load on the RTG, so I'm going to have a very high peak current momentarily that the genset may not be able to supply. And I'm going to have an opportunity when we're lowering the load, I'll have excess energy, in which case I can then charge the battery. There is a slight difference in the hardware topology compared to the centralized situation. Let's have a closer look at the integrated topology, the components, and the typical layout. In this case, the battery storage down here is now closer to my actual load. So for example, if we take the rubber tire gantry hoist, this would be my hoist motor here. This would be my inverter for my rubber tire gantry motor. I would have a battery storage here, but now I would connect that through here, which is a component, a DC to DC converter. Reason for doing that is that I have a common point of coupling right here between the hoist motor load and the DC to DC. And so if I want to essentially decouple these two loads, being able to control the charging and the discharging in the battery, I need to have this additional component, this DC to DC converter. This DC to DC converter is a buck boost type of converter, and so it also allows me to have a battery storage where the DC voltage doesn't necessarily have to match then the DC voltage required here on my main bus for my overall load. If I consider the fact that my source up here could either be a grid or could be a genset in the case of a mobile application, my DC bus voltage is going to be dependent upon that genset or that AC grid that's powering. And so my battery may or may not match the voltage necessary for that DC bus. So I will have this DC to DC converter to compensate for that. If we look at the enclosure itself, and we try to highlight each individual section. So again, I will have some kind of a converter in front. In this case, we're showing an active front end converter. It can be useful even with a genset, for example, for harmonics, power quality reasons. It could be also a basic converter, so in other words, a diode supply type of converter, particularly if you're using a genset and power flow can only come from the genset, for example. I will have an additional inverter here to control my load. And finally, the DC to DC converter. This cabinet here being the actual inverter itself, and this would be the actual filtering components. Now, what is nice about the overall construction of this topology is that the inverters themselves are all of the same, or could be potentially the same hardware depending on the sizing. So the inverters for the active front end, the inverters for the load, and as well as the inverters for the DC to DC can all be the exact same hardware. The differences are going to come in the firmware, the control, and the filtering components that are necessary. Now again, we're not showing the battery here. The battery could potentially be integrated with the enclosure. However, it is quite often separate due to the fact that it could come from a supplier in an integrated unit along with a battery management system, and it may be more convenient than for replacements due to aging, for example. So if we look at an offering from what Danfoss could provide, so Danfoss has the ability to provide all of these components within these converters. Again, the hardware, the inverter hardware itself is the same. So the same hardware we use to run a motor, we can use as a grid converter. It's available in both 500 and 690 volt voltage classes. It's available in liquid and air cooling, the same as our inverters. Liquid cooling medium is particularly useful for marine applications. And along with the inverter itself, we provide specific firmware to be able to provide microgrids and standard active front ends and connections to utility grids. Based on that same inverter hardware, we can also provide DC to DC solutions. Again, 500 and 690 volt liquid cooled and air cooled, with a particular firmware that's adopted to change the AC inverter along with a filtering solution, an inductor solution, to be able to provide a DC to DC control for batteries as well as other DC types of sources. And finally, I'd like to leave you with a little bit of sort of the growth expectations in the marketplace. This is from 2015, so we're partly through this cycle already. But the expectation at the time, and we're still seeing, is a very high compound annual growth. And this is for inverter shipments by power rating for energy storage. These two top boxes are in the higher power range, so that's 100 kilowatt and up, where you would typically find industrial and utility scale types of applications for energy storage and hybridization. So the expectation is for continued growth throughout the next few decades. So there is a fantastic business potential looking forward in hybridization. And this concludes the presentation portion of this hybridization webinar, and I would thank you for your time.
Okay, thank you, Miles, for that presentation. Now let's go ahead and take a look at some questions from our audience today. As a reminder, if you would like to ask a question, just enter it into the lower section of the Q&A window and click Submit. So our first question is, how do inverters interact with the battery system?
If we look at the overall system, particularly in the energy storage sort of value chain, there will be multiple systems involved. So we didn't go through those systems, but the equipment that we manufacture, which is the power conversion systems, has to be able to interact with all of them. There'll be an energy management system and a power management system, but on the battery side, there will be a battery management system. That system will be monitoring the charge and discharge rate, the voltage levels, the health of the system. And so the power conversion system will either be interacting directly with that battery management system, particularly if there's a DC to DC converter, or that battery management system could be interacting with a power management system in the case of energy storage back to the grid, in which case the power management system will then potentially be going back and controlling through the power conversion systems.
Okay, thank you, Miles. The next question asks, in what industries or applications do you see the most growth in hybridization?
For sure, it's in the energy storage, particularly centered around applications for stabilizations of grid, where people are looking at grids where we are microgrid opportunities where we have renewables such as the wind and the solar. But we're also seeing a lot of opportunities in applications where there may be savings in energy, such as in marine applications, legislative requirements, for example, where there may be emissions issues, and even in critical applications in industry where, for example, the industrial applications we were talking about, where you want to have where uptime is necessary to guarantee. And a lot of this is coming about in these other applications due to the reduction in energy storage costs.
Okay, great. Next question, how do the inverter systems with grid converters interact with the power system for demand stabilization?
Again, this comes back to very similarly with the battery management systems, in that if we looked at an energy storage system, ultimately there's going to be some kind of an energy management system, a power management system that will then interact with the power conversion system. So those upper layer systems are going to be monitoring the grid, and they'll provide the feedback to the power conversion systems to either request to store or provide energy, whether that's in kilowatts or kVAR.
Okay, great. Thank you, Miles. The next question is, are you providing double and triple redundancy in your systems?
That would depend. Again, we were looking at it more from a power conversion equipment. So it would require a systems designer to look at the overall redundancy and then design that in as a system overall.
Okay. Let's take a look at one more question. Are there different requirements for the transportation industry hybridization versus industrial and energy?
In the transportation, it's all about compact. So getting the energy storage systems to minimize the volume and weight. And in some of the transportation industries as well, it's about packaging. It becomes an issue in terms of, for example, in marine, you could use standard inverters, which could be then packaged into enclosures for a marine environment. But if you get into some transportation industries, such as vehicles, whether they're heavy industry, there the packaging requirements become key. Very high IP class, high vibration, high heat. So it comes down to compact size, weight, and enclosure classes.
Okay, great. Thanks, Miles. And with that, we're going to wrap this webinar up right there. Thank you all for taking the time to learn about hybridization using power converters and how Danfoss Drives can help you achieve the results you need for your applications. Take care and have a great rest of your day.